Have you ever thought about how complex applications manage to perform countless operations without constant manual intervention? From sending out daily newsletters to running nightly database backups, or even processing millions of financial transactions at specific times, there's a silent hero working behind the scenes. That hero is the task scheduling system. At its core, a task scheduling system is designed to automate repetitive or time-sensitive tasks. Imagine having to manually kick off every single report generation or data sync. It would be incredibly inefficient and prone to human error. Instead, these systems take over, ensuring that tasks are executed precisely when they're needed without you having to lift a finger. This automation is vital because it ensures efficient resource utilization. Your server's CPU and memory aren't tied up waiting for someone to click a button. Instead, tasks can be scheduled during off-peak hours or distributed intelligently to maximize throughput. This makes task scheduling crucial for background processing and delayed operations. Think about an e-commerce platform. When you place an order, the system might immediately send a confirmation email, but it might also schedule a task to update inventory levels, process payment, and notify the warehouse, all as separate background operations that don't block your immediate user experience. Good examples of where you'll find these systems include automating data backups, generating complex reports at the end of the month, or dispatching large-scale email campaigns precisely on schedule. Understanding how these systems work is fundamental for building robust, scalable applications. Next, let's break down the individual components that make these systems tick. So, how does a task scheduler actually work its magic? It's not just one big program. It's a carefully orchestrated system of interacting parts. Let's explore the core components. First up, we have the task definition. Think of this as the blueprint or recipe for a task. It specifies what needs to be done, for instance, run this Python script, and when it should happen, such as every day at 3 a.m. This definition is stored and referenced by the system. Next, we have the scheduler engine, which is truly the brain of the operation. This component continuously monitors all defined tasks and determines when they are due to run. It's constantly checking the clock, deciding which tasks are ready for execution right now. Once the scheduler engine identifies a ready task, it places it into a task queue. This queue acts as a holding area, a waiting room for all pending tasks that are ready to be processed. Using a queue is vital for handling bursts of activity and ensuring tasks are processed in an orderly fashion. Finally, we have the worker processes. These are the muscle of the system. Their sole responsibility is to pick up tasks from the task queue and execute them. You can have one worker or hundreds, depending on the workload. They perform the actual work, whether it's processing data, sending emails, or generating reports. Together, these components form a robust pipeline for automated task execution. But not all tasks are the same, which brings us to the different types of scheduling. Just as there are different kinds of problems to solve, there are different types of task scheduling, each suited for particular scenarios. Understanding these distinctions helps you choose the right approach for your application. First, let's talk about batch scheduling. This is where a large collection of tasks is gathered and then executed all at once, typically during periods of low system activity, like overnight. Think of processing all credit card transactions from a day at midnight, or running a large data analysis job. On the other end of the spectrum is real-time scheduling. This type is critical for systems where tasks must complete within very strict, often minuscule deadlines. Missing a deadline could lead to catastrophic failure, common in industrial control systems or medical devices. Here, predictability is paramount. Then we have periodic scheduling. This is perhaps the most common type you'll encounter in web development. With periodic scheduling, tasks run at fixed, recurring intervals. You might schedule a task to run every hour, every Monday morning, or once a day. This is perfect for things like refreshing cache data or sending daily digests. Finally, There's event-driven scheduling. In this model, tasks aren't tied to a specific time or a batch. Instead, they are triggered by specific events. For example, when a new user signs up, an event fires, triggering a task to send a welcome email. This approach is highly reactive and often used in microservices architectures. Each has its strengths and weaknesses, and often a complex system will utilize a combination of these approaches. Now, let's consider some of the challenges you might face when building or integrating these systems. Building or integrating a task scheduling system isn't always straightforward. There are several significant challenges and considerations you need to keep in mind to ensure your system is robust and reliable. Process. One of the primary concerns is concurrency and parallelism. In a modern application, you're rarely running just one task at a time. You'll likely have many tasks needing to execute simultaneously. How do you manage these without them interfering with each other or overwhelming your system resources? This involves careful design for parallel execution. Closely related is scalability. As your application grows, the number of tasks will inevitably increase. Can your system handle this growth gracefully? Can you easily add more worker processes or resources to cope with a higher task load without redesigning everything? A well-designed scheduler should scale horizontally. Another critical consideration is fault tolerance. What happens if a worker process crashes in the middle of a task, or if the server hosting your scheduler goes down? A robust system needs mechanisms to detect failures, retry failed tasks, or ensure tasks complete successfully even in the face of component failures. Finally, and often overlooked, is monitoring and logging. When things go wrong, how do you know? How do you diagnose the issue? You need comprehensive logging to record task executions, successes, failures, and any errors. Furthermore, a good monitoring system will give you real-time insights into the health and performance of your scheduler, allowing you to quickly identify and troubleshoot problems. Addressing these challenges requires thoughtful design and often the use of specialized tools and frameworks. With these challenges in mind, let's briefly touch upon what it might look like to implement a simple one. Now that we've covered what task scheduling systems are, their components, types, and challenges, you might be wondering, how would you even begin to implement a simple one? While building a production-ready system is complex, the core concepts are quite approachable. First, you need to define tasks. This typically involves storing the details of each task, what function it should run, what parameters it needs, and its schedule in a persistent storage like a database. Next, you'd implement a polling mechanism. This is your scheduler engine. It's a process that periodically wakes up, queries your database for tasks that are currently due, and identifies those ready for execution. It's like a clock watcher, constantly checking if it's time for a task to begin. Once a task is identified as due, the scheduler doesn't usually run it itself. Instead, it places the task onto a message queue. Technologies like Redis, or RabbitMQ are excellent for this. The message queue acts as an intermediary, decoupling the scheduler from actual execution. Finally, you'd have a worker pool. These are separate processes, perhaps running on different servers, that continuously listen to the message queue. Whenever a new message appears, a worker picks it up, executes the defined function, and then potentially reports back the status. You can easily scale your worker pool up or down based on your workload. This basic architecture provides a foundation for handling automated tasks. From here, you'd add layers of sophistication, like error handling, retries, and monitoring. This concludes our lesson on task scheduling systems. I hope you now have a solid understanding of this critical aspect of modern software development.